All right, let's get started. I opened up the iClicker class, so you should log in now and join, and then later I'll push some questions to your devices. A couple of anticipated announcements. I'll talk about the exam on the next slide, but for now, the next Achieve homework is posted. There's only one Achieve homework for Chapter 2. That's going to be due Monday at 9 a.m. Chapter 2 is on our exam on Wednesday, so it's a good way to practice this content. I also have posted Chapters 1 and 2 learning curves on Achieve. Let me show you what these look like real quick. So if you go to Achieve, you can't see this. Okay, if you go to Achieve and go to assignments, you'll see that was already due. Chapter 2 homework is due on Monday, and then you have Chapter 1 learning curve, Chapter 2 learning curve. They're due next Friday, so you have over like a week and a half to do them. And these are good review assignments, and they're extra credit, so you don't have to do them if you don't want to. But if you want to review some content, you can do that in these learning curves. The extra credit will go towards your overall exam grade in a class. So towards like the end of the semester, those extra credit points will be put towards your exam grades. What did I open? I think that was the Chapter 2. Yeah, so I opened the Chapter 2 one. All the different sections of Chapter 2 are in here. This is what's in the activity. If you click Begin Activity, it'll give you a bunch of questions. Your target score is at the top. So you want to get to 900 points. That's how you complete the assignment and earn the extra credit. Each question has probably 15-point value. They might be different. I've never seen a different point value, but you can see that in the corner. And then there are multiple choice questions. So select the chemical symbol for the element sodium. You can select, thank you. You can select the answer. If you need to go back to the book, there's a link to read the ebook page on this topic. You can get a hint, which will reduce the number of points, or you can have them show you the answer if you don't know it, and that's no points. If you click the wrong answer, it doesn't take away any points, you just don't earn any. So it'll keep giving you these questions as you go through it.
So if you don't get a 900, you don't get.
Right. Yes. It will not show that you completed the assignment. So you can try again, or you can move on, and then it'll give you more questions to go through. So there's one for Chapter 1, one for Chapter 2. Okay, I think that's everything on Achieve. And then another reminder, student drop-in hours, I have them today, 1 to 150, and then next Monday, 1 to 150 as well. And then, okay, more announcements about the exam. So next Wednesday, we have our Unit Exam 1, Chapters 1 and 2. You will be provided a periodic table with some equations and symbols. This is on Blackboard, so you can access it now so you know what it looks like. If you go to our Blackboard site, content, handouts, periodic table, and constants. This is what you'll be given. So I'll give you a hard copy of this. You don't need to print it or anything. You're welcome to print it just to keep for yourself. There is a lot on here. This is also what you're using in Gen Chem 2. So we won't talk about many of these equations this semester, but you will use them in Gen Chem 2. There are some abbreviations and symbols up here that might be helpful. I don't think we need really any of these for this first exam as far as the constants go, but in the future we will. And then the periodic table has all of the element symbols. It has the atomic number, which we will talk about, and the mass, which we'll talk about today and Friday. And so that's what you have. So that's on my next slide. Those you have to remember. But I'll get there in a second. Make sure you have a scientific calculator. So I'm going to walk around and make sure you all have a scientific calculator, that you do not have a graphing calculator or a programmable calculator. Those are not allowed in my class. They're not allowed in Gen Chem 2. There are other classes where you need a scientific calculator. So if you don't have one, get one as soon as possible and use that for your homeworks that you're working on. So you get used to using that calculator. There are going to be some multiple choice questions and then some short answer questions. Short answer questions will be probably just calculations. And then you can earn partial credit on those. So if you set the equation up properly, but you don't end up getting the correct answer, you can still get credit on that. You do not need to memorize any conversions. So one we've talked about is that 1 inch is 2.54 centimeters. Those I will provide to you if you need them in an equation. It doesn't hurt to remember those, but you don't have to stress about remembering them. One temperature conversion that I do want you to memorize is converting between Celsius and Kelvin. You don't need to remember the Fahrenheit or Celsius conversion between those two. Fahrenheit really isn't used that much in science, and if there is a question about it, I'll give you the equation. But Kelvin and Celsius are used a lot, and so I'm asking you all to remember it for this first exam, because in future science courses, you'll be expected to just know it. Like, you'll know that Kelvin is whatever Celsius is plus 273.15. So that's the temperature one that you should remember. And then additional thing from chapter 1 are these SI prefixes. So I have the ones blocked in orange that you should remember. Especially from pico to kilo. Above kilo, the larger ones aren't quite as common, but we definitely use all of these really often. I was talking to another professor here, Professor Evans, that does analytical chemistry, and she said she uses nano and pico all the time. So useful conversions to memorize. And remember what this is if you have a picometer, for example, then you have 10 to the negative 12 meters. Or if you have a kilometer, you have 10 to the third meters. So remember those prefixes. I will post all of this in an announcement on Blackboard later today, so you have it all written down. Questions? Okay. All right, then we will get started on our notes. So we ended Monday with this iClicker question, and I just wanted to go through how to complete this question. Most people got it right, but we will go through it anyway as a little refresher. And then we'll move into the next unit. So we're calculating the mass of carbon in a 20.75 gram sample of sucrose. In the previous slide, we calculated that in sucrose, 42.1% of its mass is carbon. So it doesn't matter how much sucrose you have, whatever that mass is, 42.1% of it is made up of carbon atoms. So if we're calculating the mass of just carbon in that sample of sucrose, remember, sucrose is 42.1% carbon. So you could simply take the mass of sucrose times, converting the percent to a decimal would be 0.41 or 421. And this will give you the amount of carbon, the mass of carbon. That works. We could also say we have 20.75 grams of sucrose, and then use this percentage, 42.1%, as a conversion, where we can say for every 1 gram of sucrose, we have 0.421 grams of carbon. It's the same calculation. This is just set up like our unit conversions that we've done, and that's totally fine to set this up like this, where we have 0.421 grams of carbon for every 1 gram of sucrose. And then we multiply these together, and we get 8.736 grams of carbon. I'm not quite done yet. We have to think about sig figs. So in our mass of sucrose, we have 4 sig figs. In our percentage of carbon in sucrose, we have 3 sig figs. So in our answer, we should have 3 sig figs, so 8.74 grams of carbon. All right. Okay, we will go on to 2.3. 2.3, we're talking about the history of the atom. So we're going to talk about Dalton's atomic theory, and then a series of experiments that were done after Dalton published his atomic theory in the early 1800s. And each of these helped science and helped chemistry progress to understand what an atom is. So at this point, researchers didn't know what made up an atom. So we'll first talk about Dalton's atomic theory, background about atoms, and then we'll talk about those experiments. So in 1807, Dalton published this atomic theory that all matter, just four points, all matter is composed of tiny invisible particles called atoms, and that all atoms of a given element have identical chemical properties. That are characteristic of that element. Atoms form chemical compounds by combining in whole number ratios. Atoms of some pairs of elements can combine with each other in different small whole number ratios to form different compounds. So this is what Dalton states in his atomic theory. If you remember when we talked about scientific methods, a theory is considered true until there's evidence that disproves the theory. So having this theory established, this caused other researchers to then investigate whether this is true. See if they have evidence that can support this theory, or if it doesn't support the theory. So we'll talk about those experiments in a little bit. I want to review a couple of forces. So we have gravitational force. That's like the sun's gravitational force holds all of the planets in our solar system in orbit. And then also on Earth, gravity pulls objects towards the Earth. So we have gravitational force, we have electromagnetic force, strong nuclear, and weak nuclear. All of these are more important when we're talking about really small particles like atoms. So we'll write here, most important Most important forces for tiny objects like atoms. And molecules. So this electromagnetic force, we have electrical force. These electrical forces can attract or repel. If we have objects with opposite charges, so something that's negatively charged and something that's positively charged, these are attracted to each other. And then if we have objects with the same charge, these repel. So this image here shows we have two positively charged particles. They have a force of repulsion between them. We have two negatively charged particles, force of repulsion between them. But between any positive and negative, they are attracted to each other. So this force of attraction across different charges. If the charge is greater, the magnitude of the charge is greater, then the force of attraction increases, or the force of repulsion increases. And then as these particles move further and further apart, that force increases as they move closer together. So electrical force, and then pretty similarly, we have magnetic force. This is applicable to charged objects in motion. So if we have a charged particle in motion that then is exposed to a magnetic force, that can impact the trajectory of that particle. So magnetic forces can attract or repel if we have opposite poles. If you think of a magnet, if you have north and south poles close to each other, they are attracted. Very similar to opposite charges. And then if you have the same poles, north and north or south and south, and you try to push them together, they will repel each other. So these repel. So this magnetic force is used in the studies of atomic structure, and we see that if a charged object moves through a magnetic field, it ends up changing, its trajectory changes, it obtains a curved path as it passes between the magnetic poles. So any magnetic field or force can impact the movement of a charged particle. Okay, so in atoms, now we're talking about, these are subatomic particles. There's really three things that we care about. There's electrons, or there's three things there, electrons. These are very small, negatively charged particles. They have an extremely small mass, and they are found in a cloud surrounding the nucleus. The nucleus is the very center of the atom, and the nucleus holds neutrons. These are neutral particles. So they have no charge. They're found in the nucleus. And then we have protons, which are positively charged, and they are also found in the nucleus. Neutrons and protons, they're both found in the nucleus, which we have on here. They also make up most of the mass of atoms. Electrons have a much smaller mass compared to protons and neutrons. So the mass of an atom is mostly made up of the neutrons and protons. So we know all of this about atoms, but we didn't always know about it. So the next few slides, we talk about a few different experiments which led to knowing and understanding this information. So in the early 1900s, we have these 4 experiments that we'll talk about. First is the gas discharge experiment. So a gas tube, I think that's supposed to say a glass tube, was filled with gas, and then a voltage was applied between the tubes. So we have high voltage, there's a positive metal plate and a negative metal plate. And so an electric field is created. In that field, the gaseous atoms were broken apart into negatively charged particles, which were called electrons. And then positively charged ions, which didn't have a name yet. And so from this initial experiment, what was concluded, the finding was that these atoms, the gas atoms, contain smaller parts that some are positively charged, some are negatively charged. They termed the negatively charged ones electrons. So that's all we know. It's negative particles, positive particles at this point. In another experiment, J.J. Thomson used a cathode ray tube to then determine the ratio, focusing on the electron, the ratio of the electron's charge to its mass. So this researcher subjected electron beams to electrical and magnetic forces. So we have this electron beam, we have electrical force, magnetic force, and then measured how much that electron beam bent, and that bending was used to calculate the mass to charge ratio. So we have the ratio of the charge in mass. So we have the mass to charge ratio, or the charge to mass ratio. It's a negative charge, which makes sense because we have an electron. The unit, the capital C there, is a coulomb. That's a charge unit, and then kilogram per mass. We have the ratio, but we don't actually know the charge. We don't actually know the mass. The next experiment, we identified the charge and the mass of the electron. So in the oil drop experiment, oil droplets, were using an atomizer, oil droplets were put into this chamber, and then were able to fall into the lower chamber, and this speed by which it fell was used to calculate the mass. And then a electrical force was applied through X-rays. We have a voltage, and that was used to calculate the charge of the electron. So we use the oil drop experiment to determine the charge and the mass. So from these 3 experiments so far, first one, we know there's a positive particle and a negative particle. Second one, we know there's the charge to mass ratio. And then this one, we find that the actual charge and the actual mass of an electron. We don't know much about the nucleus yet, those positively charged particles. So that's this last experiment. This was Rutherford discovered the atomic nucleus. So he took a thin film of gold, in the center here, and bombarded it with positively charged particles, which are called alpha particles. So these are, the foil is subjected to those positively charged particles, or alpha particles, and he had these sensors around and saw that some particles passed through directly, some were deflected kind of to the side, and some completely bounced back. So from this experiment, he concluded the distribution of charge and mass in atoms. So he says each atom must have a small core called a nucleus. And that nucleus must contain all of the positive charge. And most of each atom's mass must be concentrated in that nucleus. So although the nucleus is we have this at the center of an atom, it contains most of the mass. It's very small compared to the electron cloud, where all of the electrons can exist in an atom. So this last bullet point here says the size of the nucleus of an atom compared to the atom itself, so just the nucleus, would be like the size of a pea compared to a baseball stadium, and then that pea would have a mass of 250 million tons. So very small, but has a lot of mass at the center, and then the electron cloud is most of the space. And an electron cloud is the space or volume where electrons can exist. But remember, electrons are really small. So they travel around in this electron cloud, but most of that is actually empty space. Okay, so these experiments provide insight into the structure of an atom. There's certainly more to learn about atoms and properties of atoms. Actually, at the point of that last experiment, the neutron hadn't been discovered yet. That was discovered later. And we'll learn more about atoms, but this is a good representation of having our small nucleus with neutrons and protons, and then this electron cloud where those tiny electrons can exist. Okay, moving on to subatomic particles, unless we have any questions. Okay. So we'll think more about these protons, neutrons, and electrons. We'll be able to identify the mass number of an atom using each of those, and vice versa, and then identify what element an atom represents by using the mass number, and vice versa. So we're really going to be looking at the periodic table and information that the periodic table provides to identify different atoms and properties of atoms. Electrons, protons, and neutrons, these are subatomic particles. Different combinations of different numbers of each of these subatomic particles makes up all of the atoms of different elements. So different number of protons is a different element. Some information about protons, electrons, and neutrons here. Just that neutrons, neutral charge, protons positive, electron negative. Same charge, same magnitude of charge, but opposite in sign. Electrons negative, protons positive. And then we have protons and neutrons are approximately the same mass. Very small difference. And then electrons are much smaller. So you see 10 to the negative 31 versus 10 to the negative 27. Electrons are much smaller in mass. All atoms of a particular element have the same number of protons in the nucleus. So if you see an element, or if you're identifying an element with one proton that's always hydrogen. No matter what other neutrons or electrons are present, one proton's always hydrogen, 6 protons always carbon, 92 protons is always uranium. So you can always identify the atom or the element that you're looking at if you know the number of protons. The second bullet point says an element is identified by the charge of its nucleus. The charge of a nucleus is only made up of protons. So if you have a certain number of protons, that positive charge times the number of protons is the charge of the nucleus. So really what we're saying here is number of protons is how you identify an atom. This is called the atomic number. Or capital Z. And the atomic number for a specific element never changes. And our periodic table is organized where elements are listed in order of increasing atomic number. So this next slide we have a simple periodic table that shows all of the atomic numbers. We start with 1 for hydrogen, and then if you go left to right and top to bottom, we increase in atomic number. We have helium, and then we go down, we have 3 for lithium. Boron, if you ever have 5 protons, you have element boron. 7, element nitrogen, 9, element fluorine, and so on. So far we've talked about neutral atoms. If beryllium or boron, for example, has 5 protons in its nucleus, then a neutral boron atom also has 5 electrons. So the charge on a nucleus is determined by its number of protons. The charge of an electron is opposite in sign, but equal in magnitude to the charge of a proton, so then a neutral atom must have the same number of protons and electrons. It is possible to lose an electron, for an atom to lose an electron, then it has a charge, or gain an electron, and that would result in a charge as well. We'll talk about ions probably starting on Friday. Another thing that could change, so we can change the number of electrons for a given element. We could also change the number of neutrons, and that results in isotopes. So isotopes are atoms with the same number of protons, but different number of neutrons. So as an example, every chlorine atom has 17 protons in its nucleus. If you have 17 protons in the nucleus, it's always chlorine. But some chlorine nuclei have 18 neutrons, and some have 20 neutrons. So these two atoms of chlorine are isotopes of chlorine. They're both still chlorine, but they have different masses. So we say these are isotopes. And we can specify which isotope we are talking about by the mass numbers for each element, where the mass number is the sum of protons and neutrons in an isotope. So if we have chlorine with 18 neutrons, we know chlorine has 17 protons always. That isotope is chlorine 35, where we add 17 protons plus 18 neutrons, and we get that mass number for chlorine. So that's how we identify that isotope of chlorine. The other isotope with 20 neutrons is chlorine 37. And then you will see mass number abbreviated by the letter A. The next slide shows how we write these symbols if we're talking about isotopes or just nuclear symbols in general. X is the element symbol. So like chlorine 35 is represented here. We have chlorine. Then Z, which is the bond number, is the atomic number. That's the number of protons. And then A is the mass number, so that's the number on top, and this is protons plus neutrons. So chlorine 35, we talked about these two isotopes on the previous slide. This is how we represent chlorine 35 in using these symbols. So we have protons and protons plus neutrons there. So this one is chlorine 35. And then chlorine 37 is shown below. And you can always find the number of neutrons by doing the top number minus the bottom. That will give us 20 neutrons. Any questions so far? Okay. Another example here, we have uranium 235. This is represented up here. If all we're looking at is the symbol at the top, we can identify a lot of information about what isotope we're talking about. So we have the mass number, or A, which is 235. We have the chemical symbol U for uranium, and we know the atomic number, or Z, which is the number of protons, is 92. If we have a neutral atom, which we assume it's neutral unless a charge is specified, then the number of protons being 92 also tells us that we have 92 electrons. So we know number of protons, we know number of electrons, we know number of neutrons, which is the mass number minus number of protons. So 235 minus 92. We know the atomic number, which is number of protons, which is 92. And then we have the chemical symbol as U. Okay, we are going to fill out this table. So this is going to be a iClicker question I'll push to your devices. Just filling out some of the cells in the table. And I don't have it formatted where you can see the answer if you move along like I did last time. But looking at what information is here so far, fill out the table. So number of neutrons, protons, electrons, and then the nuclear symbol. So let me start this. And we'll do this for a few minutes. And then now's a good time to ask questions. If it is a neutral atom, and these are not specified neutral, so we have
So it's not explicitly stated.
Someone can make some fire and send it to me.
got to give it one more minute. Okay, 10 more seconds. All right, ending it now. Let's see how we do. Pretty good. All right. Looking good. We'll go over this together though. So if we have iron 54, if we know it's iron, we can find Fe, which is iron, on the periodic table. The number that is on the periodic table for iron is 26 as its atomic number. So 26 is the number of protons. All of these are, we're assuming, neutral, so the number of protons equals the number of electrons. And then if it's iron 54, that is the mass, which is protons plus neutrons. We do 54 minus number of protons, which is 26, to get the number of neutrons, and we have 28 neutrons. And then the element, or the nuclear symbol, has 26 as the atomic number, 54 as the mass number. For carbon 12, carbon is element C. Its atomic number is 6, so it has 6 protons. It's neutral, so it also has 6 electrons. Its mass number is 12. So we do 12 minus 6 for 6 protons to get our number of neutrons. We have 6 neutrons. For this last row, we have number of protons is the key information here. Number of protons is 22. If you look for the element that has 22 protons, it is titanium. Neutral, so 22 electrons, same number of protons. And then its mass number is the protons plus neutrons. So we have mass number of 48. So we have titanium, 48. Okay. Questions on these? Okay. I hope you all have more questions in the future. So each element that we have on the periodic table has its own set of naturally occurring isotopes. So we talked about chlorine. Chlorine has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. Chlorine 35 is much more abundant naturally than chlorine 37. Chromium has 4 common isotopes. Germanium has more. Tin has a large number of different isotopes. So these are all of the naturally occurring isotopes. The mass of each element that we see on the periodic table is an average of all of the masses of the different isotopes, taking into account the percent abundance of each one. So we'll do that on Friday. The other thing that I want to talk about or emphasize is hydrogen. So hydrogen has 2 naturally occurring isotopes. One is hydrogen 1. Hydrogen is element 1 on the periodic table. Hydrogen 1 has 1 proton and 0 neutrons. So its mass number is the same as its atomic number. Hydrogen 2 is hydrogen with 1 proton. It still has 1 proton because it's still hydrogen, but 1 neutron as well. This is still hydrogen, but it's often referred to as deuterium. So if you see that name, that is hydrogen, a hydrogen isotope with 1 proton, 1 neutron. All right, I think we'll just end early today. We'll stop here. We'll start with ions. On Friday, we'll finish chapter 2, and then, yeah, so the next Achieve homework is posted. You should get started on that now so that you're not doing everything over the weekend. Unless you want to do that, that's fine. You're adults. Yes. Yes.
I had sent an email to you because I was out for COVID
Oh.
last week.
Oh, okay.
So it says on my iClicker that I have only 70% and a reported absence.